Okay, another example. So this is an example of a drawbridge, right? So the question is, you have this drawbridge over here, right? And you can see this is the platform that you are trying to actually lift. It's connected with a cable at one end, right? And it is hinged at point A because this is allowed to rotate, so point A has to be a hinge. Okay, so given this drawbridge, the question is, what is the tension in the supporting cable of this 14-meter long and 11,000 kilogram drawbridge? So how do we solve this problem? Well, if the question is not saying anything about equilibrium, you can assume equilibrium, at least in Mech 101 class. All right, so you can assume that this is an equilibrium. So if this is an equilibrium, then we know we can apply two conditions. So how do we solve equilibrium problems? Well, first thing we have to do is identify the object. So the object is the platform, right? The bridge itself. So you draw an imaginary boundary around it, and you see where that boundary cuts across other elements that this bridge is interacting with. And this bridge is connected to the cable. This bridge is connected at point A to the ground, right? So we know at point A, we have a pivot point. We have a hinge joint. So point A can support reactions in both x and y direction. So in the free body diagram, I show AX and AY. Right? The moment I show AX and AY, it should come to my mind that I have to show my coordinate system. So I hat is pointing this way, J hat is pointing that way. Right? Okay. Then we have the weight of the bridge. So we show that through the center of mass. And then I have the tension in the cable, which will be along the cable. So I show that as well. Now, what do I know about this tension? I don't know the magnitude, but I do know the angle at which it is acting, right? Because the angle is given to be 15 degrees from horizontal. So I know the angle. So about this vector, this force, which is a vector, I know 50% of the information, which is the direction. I don't know the magnitude. So the question is asking for the magnitude. Okay, so I got AX, AY, I got mg and t. If this is an equilibrium, then I can write sigma f equal to 0, and I can write sigma m equal to 0, right? Now, the question is only asking for the tension, so it is judicious to choose your moment point to be point A, just like in the previous problem. So if you pick the moment about point A, then there will be no contribution to the momentum from AX and AY, right? Because AX and AY are passing through A. So that's what I'll do. I'll say sigma MA is equal to 0. In fact, not only sigma MA, if I take point B and I compute the moment about point B, that would be equal to 0 too. And I can also take the moment about point C. Let's say the point C is the center of this platform, and that will be equal to 0 too, right? But we are interested only in tension, so I can choose sigma MA equal to 0. Now all I have to do is write the moment of each of these forces, right? Okay, so let's look at mg. So mg is entirely along negative y direction, right? So if I drop the perpendicular from point A to mg, it will be what quantity? It will be L by 2, and this is 30, so this is L by 2 cosine 30. So mg by 2, L times cosine 30 is the moment of mg. What is the sign? This force is going to rotate about point A in the clockwise direction. How do we know that? Remember, you can always draw the circle that's tangent to the line of action. So this is the line of action. This is the point A. So you'll make A as your center and draw a circle such that the circle is tangent to this line of action. The force is pushing it downward, which means circle is, or the gear or the wheel, whatever you think of it as, is going to rotate clockwise. That means moment is negative, and that's why we have the minus sign here, right? Okay. So for mg, we use the perpendicular distance. Why? Because it's readily known over here, right? Okay, so now let's look at t. So for t, we will resolve it along x and y direction. We know this angle is 15, so this angle is 15. So the component of t, so let me just draw it again. This is x direction, this is y direction, and t is pointing like that at 15 degree, right? So the component of t along x direction would be minus t cosine 15, and along y would be minus t sine 15, right? Okay, so we have t cosine 15 pointing towards left, so we have 2 cosine 15 multiplied by the perpendicular distance. So perpendicular distance would be this, which is how much? This is whole length is L from here to here, and that's 30. So this would be L sine 30, perpendicular distance, right? Okay, so we got that. And the direction of this moment would be positive, because this component is pointing towards this direction. So if you draw the circle with this as the tangent, the circle is going to rotate in the counterclockwise direction, and that's why this whole quantity is positive, right? For the same reason, if you look at the component of t along y direction, which is t sine 15, this is going to give rise to a moment in the clockwise direction, and that's why this quantity is negative. So you add them together, some quantities are positive, some quantities are negative, and you equate it to 0. You have one equation, everything is known except for t. You solve for t. Right? Okay, so the question is, what if I was interested in, let's say, the reaction at A? How would I solve for that? So I want to solve for a reaction at A. The reaction forces at A, AX and AY. Anyone? Any ideas? How can I solve for reaction at A? So one way we can solve for reaction at A is we can simply write sigma f equal to 0, right? So if I write sigma f equal to 0, what will I have? I will have acceleration forces AX. I'll have acceleration force from t, which is t cosine 15, but it's negative. So that's AX minus t cosine 15, and that should be equal to 0. Since t is just known, we know the AX now. Then we can sum up the forces along the y direction. Forces along y direction are AY, which is positive, mg, which is negative, and t sine 15, which is negative. So we add them together, equated to 0. Since t is known, mg is known, we can solve for AY. So by using sigma f equal to 0, now I can solve for AX and AY, right? I can also take the moment about point B and equate that to be 0. So if I take moment about point B, there will be no contribution from the tension. There will be contribution from mg, and there will be contribution from AX and AY. But that one equation alone won't let you solve for both AX and AY, right? Because you'll get only one equation, you have two unknowns. Then you have to take moment about another point. Then since you have to write two equations, why not just do sigma f equal to 0 and solve for the problem in one shot? Right? Any questions about this?
How do you get, like, sometimes you use L sin 30, sometimes you use L cosine 30?
Well, that depends on the perpendicular distance, right? So the t cosine 15 is going this way, so I have to use this perpendicular distance. So let me erase this so that you can see it more clearly. So the component of t along horizontal direction, this is 15, is t cosine 15, right? That part you understand. So I'm looking for perpendicular distance to this line of action from point A. So how do I get that? I can extend this line, and I can draw the perpendicular. So I'm looking for this distance, right, d, which is this. This angle is 30, this angle is 30, this whole length is L, so this has to be L sin 30, right? This is a right angle triangle. For t sine 15, which is pointing this way, the perpendicular distance is this, and that is L cosine 30. So I'm looking for the perpendicular distance to the line of action. And for that, you need to use a little bit of trigonometry and geometry to figure that out. Okay, any other questions about this? All right.